Today we were going to the part two of the inference optimization for large language models. So we this presentation actually is taken from the KDD tutorial just a month ago on inference optimization of foundation models on AI accelerators from Amazon Science. And for the part one presentations, feel free to look at my YouTube channel, Yan AI Talk. So I have uploaded the first part. It's the KV cache, key value, KV cache, not KW cache, KV cache, various architectures and flash attentions in the part one covered. And also, if you are interested in the other LM topics, you can find all of our previous meetups about our past presentations for variety of models, including Llama models, like these mixture models, and also GPT from OpenAI. Yep. So this is a recap of our last session. First is like, why do we need inference optimization? It is because according to the market share projection, the inference is going to take more than like around 85% of the cost to run the inference, while the training is only 15% because the training is just one time at a very updated every month at a cadence, real cadence, while the LM inference is far more frequent to serve millions or even billions of users with low latencies. So if we are able to optimize the inference speed, first it will improve the customer experience, right? So in the interaction experience with the LM will be more friendly for the users, and also second, it's going to be save the billings, the cost billings, and also environmental friendly regarding the consumption of the energies. This is a full space of the inference optimizations. So last time we have talked about the different metrics, right? How can we measure the latency throughout the full pipeline? Of course, we can measure the end-to-end latency from the beginning to generate the first token to the full sequence is complete. And regarding the inference stages, there's a pre-fill stage, which means you need to calculate all the key values and generate the first tokens. And then the decoding stage, which you will generate the subsequent second token till the last token using the KV cache calculated from the pre-fill stage. And then with this matrix, we need to optimize these two different stages while model architecture choices, system optimization, model compression, and algorithm optimization. So some of these previous two are covered in part one. So feel free to check our recordings on my YouTube channel. And this session will mainly focus on the model compression techniques. Okay, on the model compression, first, motivation, I think is the same with why we need to optimize inference. Inference is expensive and it's slow with large models. And sometimes we need multiple chips to even to just load one big model, right? For example, the Llama 400 billion parameter models, if you load them in the native precision of the float point 16 bits, you would require like 810 gigabytes memories to load the full model in. So the key idea of model compression is whether we can compress the large model into a smaller model. Either like we can use the lower precision data types. For example, instead of using the 16-bit, like 62 or 16-bit floating data points, we can use like 8-bit or even 4-bit float or integer types. And also, if there's a way to use fewer parameters, like if we can distill a smaller LLM from a larger LLM and yet match the performance of the large LLM, that will be greatly reduce the inference speed, latencies for the models. So, but usually there's a trade-off, right, between the accuracy and the inference improvement this way. Because if you lose low precision data type, you may need to sometimes trade off some accuracy of your model's outputs with the low precision data types. So benefits of the model compression includes it will reduce the number of flops to calculate doing the forward pass for the throughout the decoder. And yeah, but it sometimes some techniques that only applies to specific set of models. It may not be general. For example, there's the technique called model pruning. I will skip model pruning because I feel it's not that commonly used. But the key idea of model pruning is like we figure out what are the less important parameters or connections in the network, and then basically at the inference time we just directly remove this connections at inference time so that the model is kind of sparser, right? It's like more sparse and the forward pass calculations are fewer. It will also help speed up the prefill. So if we are able to remove the 50% half of the parameters of the model, it also will reduce the flops computation complexity by half. And also it will reduces the memory footprint of the LM. As we know, the LM is huge, so loading them into the memory is going to be a challenge. And this type of techniques applies to, and this benefits actually applies to all model compression methods. And this number of machines we need to serve DRM can go down, and also it will speed up the prefill and also the decoding stage. In terms of the model compression measurement, we need there's a compression ratio. I think it's the same compression ratio when we kind of compress a file. We just calculate what is the unpressed model size and then what is the pressed model size. So if its compression ratio is larger than 1, it means the larger the better, right? So it means that it's more and more compressed by this compression ratio. An overview of the model compression method. So it mainly has quantization, pruning, and distillation. So quantization is all about how we can use lower precision data types, right? So instead of using 32 or 16 bit, we can use 8 or 4 bit, or even 1.5 bit. Right now, there's like a 1.5 bit LM. So it's all under like a quantization, whether we can use a lower precision data type and yet maintain a similar level of performance uh, uh, due to there's some redundancies in the LM um, knowledge. Pruning is all about whether we can just some weights are close to zero, right? Maybe we can just zero it out and just remove the collection there. So it's called a pruning. Distillation is we can have a teacher model, which is a large model, and then we can have a student model, which is a smaller size model, and we let the large model, teacher model, to train that student model. And in the end, we are just going to deploy that student model, which is a much smaller size than large model, and yet close to match the performance of the large model. So these are kind of the key ideas under different branch for the model compression. And in this meetup, we will mainly focus on the quantization and distillation. Okay, model quantization. So in order to understand model quantization, we need to understand different data points or data types. So these are very commonly used ones. like when you do the model quantization, these are very commonly used data types, like the float like 32. This is very standard. It's like without any compression, you can just use like a 32 bits floating points of the original model. And of course, you can reduce the bits by half into 16 bits. And then you see like when you reduce the bits width, the range becomes smaller, right? And also the precision is going to be also less precise comparing to the like the longer bits. But the benefits that you will gain faster inference. So this is kind of actually the range greatly reduced from the original range to the 16 bits range. And also you can use right now also people commonly use the integer bits like the 8 bits. This one is like you have a sign here and U with a U in the front is like you do not have any sign. It's just directly from 0 to 255. So integer 8 and integer 4 is commonly currently used for even more efficient inference, and especially int 8 is commonly used in the deployment. And the unint, uint, is mainly used for the images because like image pixels, etc. data, we don't have any negative values, so this is a good fit for the image network. Yeah, int4 is it's mainly I think it's mainly designed for the edge devices, right? Especially if you want to load somewhat LLM into an edge device, like not on big machine, but on say on your cell phone directly, which is like very limited in the memory. So then you can there's lots of research about how to process a smaller LLM on the edge device. So there's a lot of active research here in on the super extra lightweight models using int bit 4 or less. So this is like originally 16-bit network. If it is quantized by 8-bit, the compression ratio is 2. Or if you want to use int4 as the to quantize all the model weights, right? And then the compression ratio is 4, so you need like a lot less memory requirement to load the model weights, and also the latency is going to be improved. So what are the quantized components in the LLM? So very straightforward one is the key value pairs, right? And I think in last session we talked about how we can use key value cache to speed up the decoding phase. So the keys and the values, instead of storing them as float 32 or float 16, you can even store them as integer 8. So that will greatly reduce the memory requirement to pre-store all these key values pairs. And also the linear layers in the attention and feed-forward layers. So these are the linear weights besides the attention weights. And also the activations in the feed-forward layers. There's some difference on the activation part because these key values and weights, these are fixed. So once the model is fully trained, the key values and the weights are already fixed, right? So it won't change. It won't change depending on the inputs, while the activation has a dependency on the inputs because different inputs, the activations will be different. So that's the main change. Difference between the how the quantizing activations may be different from how we quantize like key values and weights there. And that will lead to different quantization differences. Like one is the static quantization, the other is dynamic. For the dynamic one, it only quantizes the weights, but it won't quantize the activations. While the static one, it will quantize both. usually the performance for the static quantization typically is better, but it also requires some pre-inference calibrations. This is mainly for the activation because the activation depends on the inputs, right? So basically, we need a sample from the inference data set in order to calibrate the parameter settings to how can we quantize for the activations. For example, we want to understand the range of your production, like inference data set, so that we can properly set the range for the quantization, for the activation. So this accuracy, well, static one will be higher, but it requires a calibration, while the dynamic one, there's no data, it's just quantized on the fly. Use case is for optimized inference, high performance, but this dynamic one, because it doesn't require any prior calibration with a pre data set, it is quick for the deployment and also flexible to use. Actually look at a specific example of how we can quantize a float 32 bits to integer 8 bit. Actually, the best way to show this is directly ask ChatGPT. So let me share an example from chat from what I got. Actually, I use it a lot to prepare the presentation. It gives very good examples to learn about the concept. For example, I just asked like give me a illustration of how we quantize float 32 to integer 8, right? So first, step one, define the range for float 32 and integer 8. Depending on your range of weights in your data, right? So we know exactly what is the integer 8 range is, but this one will determined by the weights in your network. Usually the weights in the network is not big. Usually it's like normalized, like and roughly between like say -2 to 2, or smaller value because it's like large values will cause issues with the gradient descent and also leading the instability of the network. So basically, we need to figure out what is the range of the float 32 values of all the network weights. First, define the range. And then we need to choose the quantization scale and 0 point. So these two are the parameters in the quantization formula. So scale is how we want to map the range from there is a range difference, right, from the float 32 to integer 8. So we want to map the full range from 32 to integer 8. And 0 point is basically we want the 0 point in the float 32 space to be the zero, like integer 0 in the new integer 8 space. So it's kind of like a shift. This is the example, right? So you see scale is pointing 0.1 and 0 point like integer 8 0 point will map to float 0 for float 32. So this is an example. Like if we have a 1.8 for float 32, and then we can divide it by the scale, which is 0.1 over here, and then plus the 0 point. So that gives us 18. So basically we map the 1.8 to an integer here. And the same, we can use the reverse formula to reverse it back to the float 32, which is the integer value, and then multiply by the scale. And then we kind of revert it back to the floating space. Yeah, I would recommend like if you want to try out like or understand deeper into a different circumstances, just directly talk to ChatGPT. I think it's a great tool to understand any new concept by Q&As directly over here. Yeah, this is just a small example to show. What I want to show here, like high level, just to understand what is the range you want to map from original data points to the new range. And then you want to apply the scale and also map the 0 point, kind of like the anchor point there, so that you can map 1.8 from the float space to an integer in your new space. And then there's also a question about when to quantize. There's quantization aware training and post-training quantization. Quantization aware training is you load in the pre-trained model, then you quantize it, and then basically you have kind of a new model, but with the different data types for each of the weight. And then you just continuously retrain and fine-tune the model based on the training data set. And that gets you the final quantized model. So this will require fine-tuning of the quantized model there. Well, the other way is does not require fine-tuning. You just load in the pre-trained model and if you do the static calibration, you need the calibration data to have an idea of what is the inference data look like, right? And then these two, you will do the static calibration. And for dynamic calibration, you don't even need the calibration data. You just directly quantize all the weights, and get your final quantized model. But as you can tell, this one usually the performance is good, because you kind of further fine-tune the model with the new data types, right? This usually can give better performance, but this one is more easier to deploy and also flexible to use. Uh, yeah, I want to specifically mention a very interesting recent work. I think it just published this year. It's like the era of 1-bit LLM. So all large language models are 1.58 bits. So this is like uh, it's not like the model size is 1 bit. Actually, it's focused on specific on the linear layer, right? So as you know, like the decoder has the multi-head attention and also have a feed-forward network. And then in each of this module, there's a linear layer. Basically, is to do the matrix transformation kind of uh, to do the say the query key value pairs and also the forward network as you can imagine this there's also linear layers in the feed forward network. So this type of architecture specifically just focus on the linear layer in the decoder, and then they replace the linear layer with the bit linear layer there. So bit linear, what does it mean? Is say originally your linear transformation. So linear layer you can think of it just as a matrix. And then you multiply it with the inputs, and then you map it to a new dimension, right? So that's what linear layer do. So if it's like a 16-bit float, it looks like this. So you got lots of high precise floating points, right? Well, here the key idea is we just decide for the linear layer, we just use this -1, 0, 1, 3 values for all the linear weights there. It looks a little bit absurd in the beginning, but it seems it can work. The LM somehow figure out that it can work. Still can match some of the performance, even if you use like a 16-bit. How do you see the advantages of this? Is like for the linear layer, you right now all the weights are -1, 1, and 0. It means that there's no multiplication needed, right? Originally, it's all floating points, and then you still need to do the multiplication and then do the sum. While over here, you can basically just do the plus minus subtraction calculations. There's no multiplication at all needed in your calculations, which means that may lead to new hardware or new computing algorithms that can specifically just optimize based on the plus and minus operations. Because the multiplication, as you can imagine, is like take more flops, while the sum and subtraction is a lot easier and straightforward. Yeah, that's a key idea about like this 1.5 bit, 1 bit LM. And actually they show that the performance, so basically the number of parameters still stays pretty much the same, but so this is the model size. So it's still well similar range parameters, but the when you load the model in memories, the memories will be a lot less because right now you just use 1.5 bit instead of like 32 or 16 bit float in the beginning, right? So here it just shows like comparing to Llama models of similar size in terms of the model parameters. It still shows the model, especially when the model size increases, like once it reach 3 billion parameters, the performance actually will on par, like comparable or sometimes even better. I don't know how they train, but sometimes maybe it can help prevent the overfitting here. But it shows that the replacing all the linear layer with the 1.5 bit actually and then re fine tune the model based on the training data set, and then the performance actually improves, or at least like comparable once the model size reach 3 billion parameters. It's I think it's quite interesting findings here. It may also mean that the LLM do not need this many do not need this precise parameter at all because the LM has lots of redundancies in the parameter itself. The number of parameters still plays a role, are important, but how precise that is, maybe that is not critical for the final performance. Then also compare the latency and the memory consumptions. So because you use a lot less bit in your linear layer, so you can see like you achieve like a 3.68 times speed up in your or reduction of your latency when you like for the 13 bit parameters, billion parameters Llama model, and the gap or the improvement will be even bigger when you are kind of comparing at a larger model size, like 70 billion or even like 140 or 400 billion parameters. And also in terms of the memory footprint here, there's also a large reduction of the memories when you actually load the corresponding models in the memories. And here it also shows like, okay, what is the benefits of it? It is able to basically run the inference with a much larger batch size, and also is able to generate more tokens per second. So you will see like throughout Q&As with the chatbot, you will see that the tokens will come out much faster, like 8 times, almost 9 times faster than the original model at the original precision data points using the 32 or 16-bit floating points. Okay, moving next to the model distillation. So I look into the model distillation history. You find something interesting is the first paper on model distillation is actually proposed by Hilton. Uh, And I think do I have a paper link? Yeah, so this is not this one. So the very first paper is to distill the ensemble of models. So if you think about like the random forest or that, so it's like an ensemble of models, or even an ensemble of neural networks like back in 2006. And people find like the ensemble models kind of have much better performance, right? And then there's the idea about, okay, can we just distill a smaller model, like for example, just distill a single model from the ensemble model and yet still can match the performance of the ensemble model. And actually it's proposed by Dr. Hinton back in 2006. So yeah, and also another paper, Dr. Hinton is specifically on neural network in 2014. And then this Bozilla, I think this one is KDD 2006. That's the first paper to specifically focus on distilling the smaller model from the ensemble of models. And even that time is not even like for deep learning models or LLMs at that time. And actually, it's a similar scenarios right now with LLMs with billions of parameters. How can we distill a small model? that can match the performance, or at least, the gap is small, like trying to close the gap of the performance between the smaller model and the large model. And at the same time, we can benefit a lot from the low inference cost of the single smaller model. The key idea is like the education, how we learn from the teachers, right? So we can treat the larger model as the teacher, and the smaller model as the student. Basically, just ask the student model to mimic the teacher model. So we want to train the student to match the teacher's performance while a distillation loss. So there's lots of papers about how we can define the distillation loss. But there's like a very common framework, a loss that is commonly used, like it's by the probability outputs. Basically, we want to match, for example, this is your data, say it's a language sequence, right? And this is the say LLM, say a llama model. And then this is the output. The output is the probability or likelihood scores for the next word, right? So it's kind of like a decoding sequence. So you actually will get a likelihood score for, okay, what is the likelihood of the next token being teacher, right? So for each of the token, you will get a score for each of the token for the next token prediction. So basically, we take this score prediction from the teacher model, and then we also will get a score from the student small model. And then the loss is we want to close the gap. Like we want the student model score to be as close as possible to the teacher model score, and then use that loss back. So if there's a difference, say from the student score to the teacher score, then we back propagate the loss there to retrain and refine the student model so that the student model can generate the scores, predictions closer and closer to the teacher model's outputs. So that is a key idea of the teacher, like one very common techniques of how we distill the model. So I will give a more concrete example later. So let me. Okay, so here, the benefits, of course, is like you get a smaller model with fewer parameters, of course, and then you will have smaller memory requirement to load the models, and also you can speed up the full, including the prefill stage and decoding stage, because your model size is smaller and all the flops required to calculate to do the forward pass will be a lot fewer than the large models. And then this is the output logic, the idea. Is actually proposed by Dr. Hinton and Jeff Dean when they are all together at Google. So this is like distilling the logic in a neural network. So this is the key idea of how they distill a smaller network from a large network. It's interesting to see them both on the same paper for NIPS. So basically, we want to compute the probabilities, like for using the softmax from the logits. So these are the kind of the words. So if you think of it as the next token prediction for languages, then each Z stands for a word, right? Likely for the kind of your vocabulary, the full set of words in your vocabulary dictionary. So basically, you are going to compute a probability for all the likely uh, word next. So we want to match this probability vector between the teacher's output and the student output. And how exactly is the loss calculated? First, Z is the output of the teacher's scores. And then it's basically scaled by a T. They call it a temperature. So basically they want to scale the Z first, and before apply the softmax. So the softmax is just exponential, apply the exponential, and then divide it by the total sum of the probabilities by all the tokens so that the final vectors kind of sum up to one, right? So they sometimes apply the scaling factor so that they can minimize the kind of the score differences over there, like doing some scaling before applying the exponential. So this is like you can calculate the softmax scores for the teacher. You can calculate the softmax scores for the student, and then you calculate the cross entropy loss. So this loss is to make sure that the Q, P and Q are similar. So if they are exactly the same, the L soft loss between teacher and student will be zero, basically. But if they differ a lot, this loss will be large. So this is a purpose of this cross entropy loss between teacher and student. There will be another cross entropy loss between the student Y, P, and the ground truth labels Y. So this is more like you include your original training labels to directly train the student model. You have somewhat like your ground truths, right? So you can still just use the normal loss to train your student model so that you can predict the ground truth labels Y correctly. And in the model distillation, it combines the both loss together, like the similarity loss between teacher and student, and the gap between the student prediction and the ground truth labels. And then they applied alpha here to combine this loss together. Yeah, so that's the key idea there. And I think the paper also shows the if you just retrain the student model with the ground truth labels, the performance is not as good as if you include the similarity loss between the student and teacher model first. Because the teacher model may be able to capture more patterns than the student when it trained through the labels, while the student model capacity is a lot less. But because the teacher model teach the student throughout the final model scores, right, instead of 1 or 0, and then it basically gives a more room for the student to grow. So that's the kind of the key idea of instead of like this straightforward 0, 1 labels, the teacher actually teach the soft labels to the student. And maybe that is why combining these two losses together actually improve the performance of the model distillation. Actually, there are many other ways how you define the distill loss. Like you can also do the intermediate weights, like you not just on the final output, the prediction scores, you can also minimize the L2 loss between teacher and student weights in the network of the selected layers. Like you want to minimize the weights differences of certain layers. You can also minimize the distances between the activations of the teacher and student. And again, the same activation, right? The activation what depends on the input. So these are like you want to minimize the like given the input, you also want to minimize the intermediate activation outputs between the teacher and the student. And this is the papers about another other distillation loss you can apply so that the student not only learn from the final prediction, but also learn from all the intermediate weights and intermediate outputs from the teacher. So that's one type. The other type is that we can do model distillation from a knowledge transfer data set. So typical approach is use an external data set. This data set can be generated from the teacher model, especially from LLM. So the idea is like we can ask the large language models, LLM, to generate high quality textbook style data, synthetic data. It's like truly synthetic data. So you can generate as many as you want as long as you have a framework, a framework for the prompting strategies to prompt the large language models to create a diversified synthetic data sets to train the smaller model. One paper I like along this idea is for the Microsoft Phi model. So if you look at like a Microsoft Phi series is specifically focused on distilling a small model from the large model. And actually the paper textile is textbook data is all you need. And then the key idea is they want to create the high quality data uh, by using the LLM, for example, the GPT 3.5, to uh, generate synthetic textbook style data with a very good education purpose textbook data to train the smaller model. And actually, they show that they are able to achieve comparable or even better performance. And then the goal of the Phi series is, can we achieve ChatGPT level capability at a 1 billion parameter scale? So the reduction of the model parameters is even by hundreds there. So textbooks are all you need. So this is the example of how of what specific text they want to generate, right? So this is like they use ChatGPT 3.5 in their paper. I think right now they can just use all the others, even more advanced large LMs. Even if it's a closed set, although right now maybe there's a license issue to use the outputs of the closed LMs to train another model. But I think for the open sourced LLMs, right? You can use all these like very large open source LLM to create the synthetic data to train the small LLM. I think there's no violation of the license there. And then this is the text they generate actually using the GPT 3.5 to show a very high quality source of text. Like this is kind of like the instruction examples and with a very nice written code snippets. So this is more like a textbook style. So they specifically prompt the LM in such a way so that the LM writes like a textbook like that will help promote reasoning and also the basic explanations and algorithm skills. And then they are able to show that the Phi2 uh, outputs larger models. At that time, I think this is what they show in the paper, and I believe right now there's lots more models that can be compared to. But at the time of publication, they compare it to, for example, the Mistral 7B, they compare it to the Llama 2 on a variety of different tasks for coding, math, language understanding, etc. And they specifically notice for math and coding, they directly see a boost in their performance due to this textile high quality data input, because that input actually gives more straightforward reasonings and guidance and these algorithms understandings to teach the small model to solve the math or coding problem. Language understanding, as you see, is still not beating that, right? Maybe language understanding is not as strict at math and coding. The reasoning is harder. Uh, like if you follow the step, you can get it right. Maybe for math and coding, well, the language understanding is more like a soft skills. That is my interpretation. And large models will still benefit more from the language understanding. Well, for the math, coding, and the science specific subjects, if you give the right guidance and steps, maybe the small models will even exceed the performance of the large models there. Uh, they also compare Phi 2 model at that time with the Gemini 2 models at a comparable size, slightly lower size, but they also able to show some improvements across some tasks. Not all tasks. I think they specifically just list the tasks that they are able to show that Phi2 is able to achieve some improvement there. Yeah. So that's a Phi model. I think Phi model is also open sourced. So if you need like a small model to begin with, you can also check the Phi model from Microsoft. Yeah, that's the end of today's talk. So maybe we focus on the model compression and more specifically in quantizations and distillation. So quantization is all about data types precision. How can we use 30 like from 32 to even four integer data types with lower precisions and yet still able to show a comparable performance. And also distillation, what it matters in distillation is the distillation loss. Basically, what level you want to match the student's output with the teacher output. You can just directly match at the final prediction score, or you can also match it at intermediate layers and activation outputs.